IBM research, and we'll be talking about improving accuracy, privacy trade-off via model reprogramming.
Thank you, Vladio, and thank you for having me. So a few words about myself, right? So before joining IBM and working on trustworthy machine learning, I was actually trained as a signal processor. And of course, my information theory skills has been very rusted now. And then probably you can sense I'm working on AI and deep learning now because I'm using PowerPoints to do my presentations. Okay, but nonetheless, I'm going to try to show you something I'm very passionate and excited about, right? It's called the model reprogramming. And I'm going to walk you through an example of how to use this model reprogramming to improve task performance, especially accuracy, given differential privacy constraints. And then I'm going to show you what are the existing available theory to explain the success of model reprogramming. And finally, I'm going to pose a challenge and also a humble request, right, to everyone in the room, right, to ask for developing information theoretical tools to tackle and understand the theoretical limits and foundations for this problem. I believe there's a lot of things we can do together. Okay, so let's start with what is model reprogramming. And I want to have a small detour to this foundation model, right? So no matter you like this term or not, right, this is something coined by a bunch of Stanford researchers last year, right? Basically signifying a new era and a new machine learning paradigm that we have witnessing, right? It's a pre-training and fine-tuning paradigm. So there is a foundation model that is pre-trained on very large scale data, like Wikipedia scale, to learn the general representations of different modalities. And once you have that foundation model and also their generic representations, you can efficiently fine-tune it on different downstream tasks with labeled data. Right, so when I was giving a tutorial at the New Rips in December, right, at about the same time, ChatGPT just released, and we literally need to spend like 10 pages of slides to explain to people why it's foundation model, right? It uses the self-supervised learning to do pre-training and how does it do fine-tuning. But now, right, I have a very information optimum way to share what is foundation model, right? So the first question will be, okay, have you heard of ChatGPT? And then they will say yes. And then I will say, okay, so GPT-3 is the foundation model. And then ChatGPT is the fine-tuned foundation model on a chatbot application, right? So information optimal way of explaining what foundation model it is and why now so much of the AI focus is on these foundation models. So from our perspective, right, with those foundation models, right, we are basically giving a pool of available pre-trained models. Right, so we are asking the question of how can we build upon these pre-trained models to do something else, right? To solve different tasks, especially the tasks in resource-limited domains, right? So essentially, what we are proposing is a new framework of model reprogramming that basically take a pre-trained model and then we froze it, which means we are not changing the weights during the fine-tuning stage, and instead, we are inserting two, trainable layers, right, or transformations, if you like, at the input and output of the pre-trained model. To repurpose the model to do something new and do something else. And we have several examples like reprogramming speech models to do time series classification, reprogramming English language models to do molecule learning, and also reprogramming computer vision models to do biomedical measurements classification tasks. And this is really exciting because this model reprogramming actually offers a very good parameter efficiency and reusability, right? So comparing to different machine learning paradigms, right? Foundation models, it needs to train on a very large amount of data and also have billions of trainable parameters. And similar thing for task-specific learning, right? But with model reprogramming, because we only need to train the parameters of the layers we inserted, right? It's very, very parameter efficient, and you can kind of understand why it also benefits differential privacy as well. And I was very excited about this topic and wrote a survey paper on this direction as well.
Your slide is all last week. Just released a 1 trillion parameter model.
Very true. Okay, so I would like to quote Sir Isaac Newton, right? If I have seen further, it is by standing on the shoulders of giants, right? And I think this pretty much well describes what is our expectation about foundation model and the relationship to reprogramming, right? So it is true that in some data-rich domains, right, like image, text, audio, code, right, there are abundant data and we can train foundation models. But that is not the end of the story. There are regimes and scenarios where we only have limited data, right, like biomedical image tasks. There are cases where in some domains, there are simply no good pre-trained model exists, right? Or there are scenarios where a researcher cannot afford the cost of training a foundation model from scratch, right? Limited resource. Or there are some training constraints, right? Like, for example, those imposed by differential privacy. in those scenarios, right, I believe we need a new alternative, right, a resource efficient way of fine-tuning this pre-trained model to unleash the power of a foundation model to do these new tasks. Okay, so let me show you one example of how costly these foundation models can be, right? So this is an example of ChatGPT, right? So this is basically every foundation model is trained on large-scale data, and then with a high capacity, billions of parameters, neural nets. And then with that, we can fine-tune on different downstream tasks, right? So GPT-3 as an example, right? It is trained on 1,000 billion tokens and with 175 billion training parameters. And the estimated training cost is 12 million, right, to train such one foundation model. Now, right, we are entering the GPT-4 era, right? So according to some recording from the OpenAI CEO, right, Sam Altman, right? So people are estimating the cost of training GPT-4 is about 100 million, right? But at the recent event, right, Sam actually said it's more than 100 million, right? So it's pretty much very, very expensive to train such a foundation model. Okay, so as already I described, the settings I already described is that in the standard setting, right, if we have abundant resource, right, we can afford this pre-training and fine-tuning strategy. But here we are focusing on this resource limited setting, right? We want to use these foundation models to solve a new task, a new machine learning task in a new domain, especially in a resource limited domain. In this case, we are doing reprogramming instead of doing standard fine-tuning to fine-tune the weights of the foundation model. And you may now ask me the question, okay, so how is this different from transfer learning, right? So it depends on what do you mean by transfer learning, right? But my view of transfer learning is the standard view, like you take a pre-trained model with the pre-trained weights, and then you are going to fine-tune some of the parameters in the pre-trained model to do a downstream task. On contrast, right, model reprogramming, we are doing things in a different way, in the sense that we are not changing the pre-trained model weights all the way to the end. And we are really taking a model trained on domain A to solve a different problem in domain B. And these two domains, right, can be like very unrelated, right, like this time series and speech example I showed you earlier. Okay, so finally, before I go to the technical details, I also want to show some backgrounds, right? So this reprogramming idea was originally cast as the adversarial reprogramming. Because at the time, right, they discovered that it is possible to reprogram a pre-trained model to do something else, right, something new that is not originally designed by the model developer. So there were some concerns about how attackers can repurpose a pre-trained model to do something else without the consent of the model developer. And in the first paper, right, published in 2017, they show some works of reprogramming the ImageNet model, right, to do some MNIST or C510 classification problems. But if you look closely, the accuracy are kind of get only mediocre accuracy. So there's nothing interesting to explore other than, you can successfully reprogram a model to do something else. Okay, so now with these more powerful pre-trained models, like foundation models or pre-trained models or not, right? How can we leverage these powers and to do more interesting tasks? Also, especially with reprogramming. So I'm going to show you an example using a framework that we propose called the black box adversarial reprogramming. So it's a way of reprogramming a black box model to do something new. So the setting is like this, right? We are given a pre-trained model, right? In this case, even a black box model. Black box meaning you can only get to observe the output of the model, right? Like a classification API, and you will never know what is the architecture or weights inside that model. And we are trying to ask, how can we reprogram this model, right? Reprogram API, right, to do something new, right? For example, reprogram an ImageNet pre-trained model to do biomedical classification tasks. So let me use this figure to explain how this work is done, right? In the illustrative example, right? So we are given a pre-trained model, like here, ImageNet model, and given any input, it will output a prediction on all the ImageNet classes. Now we are given a downstream task, right? And in some data sets from a target domain, and then the task can be very different, right? So for example, those are biomedical image classification tasks. Now, how can we leverage this pre-trained model to help us solve the problem? So there are essentially three steps, right? The first step will be this input transformation step, right? So the first thing we will do is we will put the target data at the center of the inputs of the pre-trained ImageNet, and then we will also leave some boundary to be a trainable parameter, right? Some sort of input transformation that is trainable. right? So, and then we get a transformed data input for the target domain. The next thing we will do is we will pass the data to the pre-trained model. And of course, the predictions, right, of those transformed data inputs will be on the ImageNet class label space. So the next thing we should do is we should map the source label to the target label, right? So we should specify, okay, for these sets of ImageNet class labels, we are going to map it to a downstream label. Here ASD means the autism spectrum disorder, right? It's a binary classification for one of these data sets. And I'm going to map the other set of the classes to the second class, the non-ASD class, right? So end to end, right? I get a model that is working on the target domain, right? It starts from taking the input in the target domain and then predict something at the target label space as well. So finally, the third step is I'm going to train whatever trainable parameters I introduce at the input and output to minimize the loss that we design for the target domain. And this training, right, can be done in a black box way if we are dealing with a black box model, right, using like zeroth order optimization or any gradient-free techniques that Tara, the first day's keynote speaker, talked about. And noticeably, in the entire process, right, we are not requesting to change the weights of the pre-trained model. All we do is to insert these new modules at the beginning and end of the model, right, to enable this sort of transfer learning scenario. But I prefer to call it reprogramming. Okay, so mathematically, right, it's actually pretty simple to formulate, right? So we are given a pre-trained classifier. It can be a black box model, a black box function that basically take any input, right, rescale between minus and 1 with dimension d, and then it will output predictions, right, like a softmax outputs over the k classes, right, in the source domain. And now we are given a set of data from a downstream domain, right? We are assuming the target data has a smaller dimension than the source data, so we can allow some extra space, right, to introduce these trainable perturbations. Yes.
So you assume that the output of the classifier is over the rails, not just like a score on 0 to 1.
Yeah, it actually doesn't matter, right? So if you look at the logits, right? So before taking the softmax, it's a real value, but after taking log, it can be 0 to 1. So it doesn't really matter.
Okay, it's just a matter of what you get as an output of the black box.
Yes, yes, very true. Okay, so those are the set of trainable parameters that we introduce as a universal perturbation to every target input. Okay, so mathematically, right, we are given this target data, right, Ti, and then first thing we will do is we will zero pad the target data to make sure the padded image will have the same size as the ImageNet data, and then we will introduce this trainable parameter, the perturbation P, right, which is nothing but this mask function, right? So we are basically introducing a mask asking the model to add perturbation only to the border, right? Or you can add the perturbation inside the image as well. But basically, our empirical results suggest that the best way you should do is to put the target data at the center of the inputs and also only train those border parameters, the pixel values. That is usually the best configuration. So this W will be the universal trainable parameter. And of course, you can consider more complicated setting, right? Even introducing a small neural nets, right, to introduce this input perturbation or transformation functions. So how do we map the outputs, right? So the easiest thing that we can do is to do random mapping, right? So you can randomly assign some source labels to map to a target label, right? It's actually a mapping that you can design, right? So for example, here, I'm basically saying the prediction outputs or the model output of the ASD class will be the average of the 3 source class images, source classes, tench, goldfish, and hammerhead. We can do something even slightly sophisticated, right? So before we do this label mapping, right, we can just feed in those target data and observe what is the best responded class in the source domain, and we can do sort of this frequency-based mapping, and normally that will improve the accuracy as well. Okay. And once we have the mapping and the input transformation, the final thing is training, right? So here we can take any preferred target domain task, and then we can train those parameters that we introduced right here, the input, the perturbations, parameters by W. And then the training depends on the scenarios. If it's a black box, right, we will use this gradient-free based method to update the weights until it converges. If it's a white box, right, then we can just simply use the gradient-based approach, right, to optimize the parameters associated with the information transformation block. So that is basically a simple example of how this model reprogramming is working for this image classification task. And as I indicated earlier on, right, this is a very general framework, right? So we have applied this technique and this principle to different modalities and different applications. And they can be all summarized into these high-level algorithmic procedures, right? So we are given a set of target domain data, and then we can initialize the input perturbation, input transformation and output mapping layer with some parameters theta and w, right? And then you do this input transformation and output mapping through some learning mechanisms and training mechanisms, and then you only train this theta and w, right? The two sets of parameters that you introduce to reprogram a pre-trained model, and finally you will get a reprogrammed model for your downstream task. Okay, so this is and the next two slides I'm going to quickly show and convince you that this is actually a very nice alternative to solve problems in a resource-limited setting. So this is the ASD classification example I talked about previously, right? So this is a binary classification task, and each class only have about 500 images. And these are actually the brain correlation graphs obtained from real measurements. So they are very expensive to annotate and to collect the data in scale, right? So what we can observe is that the AR means a white box reprogramming, and BAR means black box reprogramming. So both cases, right, actually achieve the state-of-the-art results on these data sets, and they perform much better to comparing to training from scratch and even simple transfer learning. And they also outperform the state-of-the-art results that actually requires very complicated hand-designed learning rules and feature learning process. So we can see that by simply leveraging the model pre-trained on another domain, right? In this case, the general image classification task, right? We can already apply these tools to solve these problems and achieve new state-of-the-art in these resource-limited domains. And as I mentioned, this work also this method also works for black box models, right? So one interesting experiment that we do is we upload a traffic sign classification data set to Microsoft API, and then this is a kind of the auto machine learning setting where they will give us a model, right, to predict the to predict any images with these traffic signs, but they will not let us know what is the model architecture or the weights. In this case, right, we can also reprogram this API to do ASD classification, right? So if you spend like $20, then you can get the ASD classified with about 67.8% accuracy, which is actually a very cost-effective solution to use state-of-the-art models, right, for solving your difficult problems at hand. Okay. And finally, I would like to make some remarks about the connections between model reprogramming and prompting, right? So prompting is, again, another parameter efficient way, right, to play with the state-of-the-art machine learning models. So my definition will be, in computer vision domain, if your source model and your downstream tasks are both from the computer vision domain, then model reprogramming is basically the same as visual prompting, right? So kind of independently, about 2 years ago, right, independently, a group of researchers from MIT, right, invented this word, visual prompting, right? So what they are doing here is, again, very similar, and then they actually add adversarial reprogramming as a baseline as well, right? So you add some visual prompt here. The visual prompt is nothing but these input transformations that we introduced in the model reprogramming framework, and then they are going to also assign some output label mapping to solve a downstream task. What's more interesting is that they also show this thing is also doable for CLIP, right, which is the state-of-the-art text image joint encoder model. So they can reprogram by adding some visual prompt, but you can now ask the model to say this is a photo of something, and with that, right, with these simple prompting ideas, right, you will get a very high accuracy for those CLIP models. So in the recent work, we also keep exploring the benefits of the importance of this label mapping, right? So in the recent work that we are going to present at the CVPR next month, is we figure out that the iterative label mapping is actually a key to achieve the high accuracy for model reprogram, right? So this is kind of the runtime example during training time, right? So given this target image, right? So for example, a marigold image, right? And then we keep asking the model to find the best matching label according to from the source label space to the target label space. So you can see as the training loss becomes a chance to converge, right? You kind of find the best source label that maps to the target label with high semantics, right? So you can map this orange class to the marigold target class because they have a high similarity and also semantics in the space of their representations. And also similarly, this tree puppy, right, also can be mapped to eagle, right, because they share some high level similar semantics. And there are more examples in our slides on different downstream tasks. But the most interesting thing is that on Clip, right, we can also do the same thing by treating different prompt templates as a source label. And then you can ask, okay, given the target task and given the target label, right, what is the best prompt template I should use to improve the accuracy of prompting? Right, so in this case, compared to the naive visual prompting, right, with this iterative label mapping, by finding out the best prompt templates, we can actually improve the accuracy by a significant amount. And also, if you look at the data scalability in terms of how many data you have to do visual prompting or reprogramming, right, this iterative label mapping always give you a significantly better accuracy compared to using a fixed label mapping. Okay, so how is this? Yes.
Usually, when we do prompting, the learnable prompts are in the natural language part of the input, not the visual part of the input.
Yes, yes. So what you are describing is what they call a prefix tuning, right? So prompting was, you are totally right. The prompting was originally proposed in natural language processing. But when it comes to computer vision, right, people are asking how do we do prompting, right, in the computer vision space. That's why they invented this visual prompting, right? So you can now think about these trainable parameters being some sort of prefix token that you inserted, right, to prompt the model to solve the task.
Yeah, even in the vision language models, usually I've seen people insert the prompts in the text portion,
yes,
the learnable prompts.
Yes, yes, yeah. So there are also more advanced method called the visual prompt tuning, right? So in this case, if you are using a transformer here, right, then you can look at the token embeddings and insert some trainable tokens to do visual prompting, right? But here we are simply looking at the input level of tuning. But this is a great question. Okay, so how does this have anything to do with differential privacy, right? So now we want to explore the potential of using model reprogramming, right, in the field of differential privacy fine-tuning, right? So the setup is, again, I have a pre-trained source model that is trained on non-private data. And now my downstream task, right, is some privacy-sensitive data, and then I'm going to train the model to maximize the utility on the downstream task, but with some differential privacy constraints. Right, and we can compare different approaches, right? Like we can use a model reprogramming to do so, right? By introducing again the input and output trainable layers, or we can do full fine tuning, right? Which means you need to fine tune every pre-trained model weights. We can also do this partial fine tuning where you only fine tune the last few layers of a pre-trained model, right? So those are like a valid baselines, and of course we should also compare to training from scratch, right? Not using a pre-trained weights at all. And the notion of DP we are following is like a very standard epsilon delta DP. I guess you are tired of it, so I will skip the definition. Okay, so we can also extend this case to both centralized and federated learning setting, right? So in the centralized setting, right, we are training a model with a privacy budget. In the federated learning, right, we can still use this noisy SGD ideas with clipping, right? So we do some noisy SGD and clipping at the client side. And at the server side, right, they are basically doing the same standard federated averaging protocol by averaging the noisy gradients they collected from the clients and exchange those average gradients back to the clients to do federated learning. So the reprogramming idea, right, fits pretty well in both schemes, right? So for the federated learning setting, we are basically asking the clients to initialize, right, their local version of the reprogram model using their local input and output layers. And then throughout this federated learning protocol, they will learn global input and output transformation layer. And that could leverage the privacy budget better. So here are some very simple examples to show how well, right, this idea performs, right? So on the x-axis, I'm plotting the epsilon, the privacy budget. And on the y-axis, I'm comparing the accuracy of different training pipelines, right? Model reprogramming, the red one, full fine-tuning, right? Actually, the worst one because there are too many parameters to train. Also same story for train from scratch. And the only competitive method is this partial fine-tuning, where you only fine-tune the last layer of a pre-trained model. But still, you notice a very big gap between model reprogramming and standard transfer learning in both cases. Okay, so beyond DP-HGD, right, we can also adapt this model reprogramming to different DP training mechanisms, right? So another popular option will be the Pate, right, method introduced by Pevernat and others. So for those of you who are not familiar with Pate, right, this is a semi-supervised machine learning setup, right, where you first separate your private data into several disjoint sets, and then you train what is so-called teacher model on those disjoint sets. And then you are also given a set of unlabeled data, and then you are going to use those teacher models to give a prediction on the labeled data set and use that as a distillation process to train your final student model. And this is arguably a better way of leveraging the privacy budget. And usually get a better accuracy if you use Pate instead of DP-HGD, although the setup is not quite the same. So how does the model reprogramming play a role here, right? So we simply replace the teacher model, right, used in Pate with this reprogrammed teacher model, right? So when we are training those teacher models, we are again only using this visual prompting or input transformation idea plus some trainable label mapping function instead of training the teacher model from scratch. So this idea is pretty simple, but the result is very significant. But I should also ask Peter to audit our performance for sure, right? So on the simple CFAR10 example, right, and when we use the models pre-trained on ImageNet, we actually get the state-of-the-art results using this Pate plus visual prompting idea or Pate plus reprogramming ideas. And of course, right, the quality of the pre-trained model takes a very significant role, right? So we do some ablation study by taking different models pre-trained on ImageNet, right? So like from like a typical convolutional neural nets, ResNet, all the way to more recent transformer-based architecture like swing transformers. And what we do see is that the more capable, right, models, right, those source models with better accuracy on their original source task actually also delivers a better accuracy privacy trade-off in the downstream task, right? So given the same epsilon budgets, right, a more advanced, more accurate source model will give also a better accuracy on the target task. We also show something on the cross-domain task, right? So if you think ImageNet and CFAR10 are too similar, we can actually do this reprogramming from ImageNet models to do blood amnesic classification task. And in this case, we are even seeing a more significant gain compared to this standard transfer learning DP-HGD results. Yes?
Do you compare your reprogramming with other with fine-tuning methods?
Yes, that would be like this one. So this transfer Pate, right, is basically taking the pre-trained model and only fine-tuning some layers.
But fine-tuning layers is not the only way. Like there are like lower type of.
Oh yeah, yes, yeah. LoRa is something that we are investigating, but I haven't had the comparison yet. But I would expect it also benefits from. It will also improve privacy accuracy trade-off for sure because of the parameter efficiency. Okay. So, just out of curiosity, we want to know why model reprogramming works. And we have a very preliminary results of why model reprogramming works, right? So this is not really about knowledge transfer, right, that people talk about in transfer learning, because we have shown model reprogramming can work well in these cross-domain learning setups, right? So some theory that we cooked out is that the target risk, right, the loss on the target domain is actually bounded by the summation of two terms, right? The first thing is the source risk, basically translating to how well your model is on the source task, right? Like what we have shown in the previous slide, like a swing transformer did better than other neural nets, right? Because it has a better accuracy on the source task. The second loss, which is the most interesting one, is called the representation alignment loss, right? So intuitively, if we are going to reprogram a dog versus cat classifier to another binary classification task, right? So what is the optimum way of reprogramming is to learn how to align one class label to dog and the other class, right, to cat, right? If we have a perfect representation alignment, then we can just reuse the classification rule of a cat and dog to solve the new binary classification task, right? So if the representation alignment between source and task labels data are perfect, then we basically can make this term 0, and then we can ensure that the target risk is upper bounded by the source risk. So this is just some numerical validation, right? So when we train the reprogram models, when we get high accuracy, and I would like to focus on the third row, right, which is the slice washer stand distance between the source data and the reprogrammed target data's representation. So you do see that when the accuracy goes high, right, the distance, right, statistical distance between these two sets of distributions become closer, which means the representation alignment loss, right, is actually lower. So this is implicitly model reprogramming is learn how to reprogram or align the representations from the target domain to the source domain. And this is just some t-SNE plot, right, to convince you that the before and after reprogramming, we do see this clear separation using reprogramming, and it actually gives a better separability in the representation space when you compare reprogramming to transfer learning. It's like a t-SNE plot, t-SNE plot, so it's like a nonlinear projection, yes. Okay, so in the interest of time, I'm going to skip this slide, but this is just like a formal theoretical statement of what I just described. Okay, so finally, right, I think the most important page, right, a humble request and ask for information theorists, right? So, you know, when I present this reprogramming ideas, right, I was thinking about this channel theory, channel capacity, and this source coding and channel coding that I learned, you know, through my graduate studies, right? So, you know, interesting question to ask is that can we formulate, right, this reprogramming problem as a way of understanding channel capacity, right? So now we have a pre-trained and frozen, right, pre-trained model, right? So we can view it as a channel, right, like a given channel. Now your input, right, will be a downstream task and data you want to solve, and the output will be a reprogrammed model. So the interesting thing to ask is that, so what is the capacity? What is the limitation of this pre-trained model, right? What tasks can be reprogrammed and solved successfully and what not, right? And what is the best way, right, to compress the source data so that the pre-trained model, right, can learn better. And in terms of a given one channel, right, so what is the best way, right, given some constraints, right, like differential privacy or any like a noise constraints, what is the maximum achievable performance, right, that can be done using reprogramming. So, you know, my guts tell me like the information theory tools should be very useful to answer questions like this, right? Given that now we are not changing the weights of the pre-trained model at all, right? So we can now pretty much think of it as a given channel. And the challenge is like to understand what this channel provides, right? And what tasks can be learned through this channel and what cannot be learned through this channel. Okay. So some simple takeaways, right? I basically present to you a new fine-tuning alternative called the model reprogramming. And it has shown a lot of empirical success in many different domains, especially in these privacy constraint fine-tuning scenarios. And it is truly 100% compatible to existing DP training methods. And I basically would like to have more discussion in terms of what can be done in terms of the theory, understand the limitations, and build new foundations for these new parameter efficient tuning pipelines, and including like LoRa, like Ilya just mentioned. And finally, this is a slide for codes and references, but I will stop here and open the floor for questions.
We have time for a couple of questions.
I have a question. So can I look at this model reprogramming? Forget the front end. Of course, you're having the front end. The back end, is it just training a last layer? Or I mean, what are you already have just one output of maybe softmax K. So you're just massaging that?
Also the input, you also need to do something at the input, because sure, when you massage the input, right, it will change the representation in all the subsequent layers. And that actually adds a lot of power to align the representation comparing to only add something at the end of the model.
Is that theorem that you have like
yes,
formal theorem, the informal theorem really based, because I'm surprised you have an upper bound. And you claim that you can actually get the target first to be less than the source. So I find that a little surprising.
Yeah, only if the second term goes to 0, right? So the interesting thing is how can you design input transformation, right? So learn this delta such that the source representation, right, will be totally aligned to the target representation. So if you have a perfect alignment, then this washes time 1 distance will be 0, and then you can guarantee the target loss is upper bounded by the source loss. But that is the ideal setting, right? So in practice, right, when we may actually measure this washes time 1 distance, right, it's actually never 0, just will become smaller once you enable this reprogramming framework.
Yes. So
Following up on Lolita's question, actually, are you using just a grouping of labels, or are you doing a weighted average of the scores there on top? I just didn't understand what.
Yes, so that is more on the implementation side. So we introduced like a label mapping, right? But also for this federated learning scenario, we are actually using a linear trainable layer instead of label mapping, right? So it really depends. So it's actually it matters of how you implement what we call an output mapping label. So it can be like a non-parametric, like assigning source labels to target labels, or you can just simply add a linear transformation layer to learn the mapping.
okay, let's take the speaker again. Poster session now, and the doors in this building will lock at 5 p.m. So the poster session ends at 5:30. But if you leave after 5, you probably won't be able to get back in. Someone opens the door. So be aware of that.
The food is going to be served upstairs.